So the titrations we have been mentioned so far are mostly you're using color to tell the endpoint, right? And from last class we talked about precipitation, and precipitation is when you're forming something insoluble. In titration, you can also do precipitation titration. So for example, if you have analyte, which is iodide, in your solution, you can add a titrant, for example, silver. And silver will react with iodide to form an insoluble compound, silver iodide, which is a precipitate. Okay. Now, the concentration of the free ions in the solution can be determined with electrochemical measures. So for example, potentiometric measurement, meaning that you're putting 2 electrodes into the solution and measure the difference between the 2 electrodes. And the potential difference is actually affected by the concentration of ions in the solution. Okay? We will talk about this in electrochemistry chapter, but just to let you know that you can use indicator, or you can also use other methods for determining the titration endpoint. For example, potentiometric methods. And actually the pH meter based titration is also based on potentiometric. The potential measured is dependent on the concentration of hydrogen ion in the solution. Okay. Anyway, we know that when you're doing titration, you can draw a titration curve, right? And in the precipitation titration case, you can also draw a titration curve. And what we have here is the x-axis is the volume of silver ion added to the solution. So remember, silver is your titrant. So the x-axis is the volume of titrant you added to the solution. And the y-axis is determined as PAG plus. Can anybody guess what is PAG plus? The precipitation.
The log-based concentration.
That's right. So it's negative logarithm of the concentration of silver. Okay. Right. So let me ask you this way. When you see a higher, for example, 14 versus 2 for PAG, which one indicate a higher silver concentration? When you have PAG equals 14 versus PAG equals 2, which one indicates a higher silver concentration?
2.
2, right? Because this is a negative logarithm. So PAG2 represent for 10 to the negative 2 versus PAG14 is 10 to the negative 14. Right? And you can see that we're not caring about the 3 different lines yet. The 3 different lines are for 3 different situations when you have different initial concentration of iodide. Okay. Let's just look at the middle one, for example, at 0.01 molarity iodide. So initially, you have excess iodide in the region, if you look at this part. So from here to here, you have excess iodide in the region. And because of you have excess iodide in the region, even though you have an equilibrium here, okay, you will have very little amount of silver because you have a lot of iodide in the region. If you also have a lot of silver, they will precipitate, right? So initially you can see that your PAG value is relatively high, right? And then we come to the equivalence point. When the equivalence point is reached, all the iodide theoretically is being reacted with silver. So all of them will go to the precipitation. But in reality, we know that when you have an insoluble compound, actually, it will be very small amount of them being dissolved in the solution, right? And this amount is determined by KSP, which is silver ion multiplied by iodide. So at the equivalence point, theoretically, all the compound will go to precipitate, but actually we will still have equal amount of silver and iodide present in the solution, even though the amount is very tiny. Okay? And you can see that the silver concentration actually increased, okay? Because the iodide concentration keep decreasing, so the silver concentration will keep increasing, since their product of these two quantities is actually a constant value. And then after the equivalence point, it's the excess silver region, meaning that because all of your iodide has been reacted, so if I keep adding silver ion into the solution, we will have more and more silver accumulated in the solution. And you can see that the concentration of silver will gradually increase to relatively high value compared to the beginning, right? And we already talked about this. The px is defined by negative log x. High values of px indicate very low concentration of x, and low value indicate relatively high concentration of x. And we have three regions, as I mentioned. You have before the equivalence point region, at the equivalence point region, and after the equivalence point region, okay? Now, there is a bunch of calculation involved to this. We won't have time to finish it today. I will cover this next class, next lecture. Is that when you have three different cases, before equivalence point, after at the equivalence point, and at the equivalence after the equivalence point, you will, if you want to calculate the concentration of the analyte or the concentration of the titrant, there are different ways, okay? At the equivalence point is probably the simplest because we have equal amount of these two. So silver and iodide have equal amount. They will just be the square root of KSP. That's the easiest case. But before and after, you have either excess analyte or excess titrant. The idea is you have to calculate the amount, the excess amount of either analyte or titrant. And then based on KSP, you calculate the concentration of the other part, okay? But we won't be able to finish it today, so we will continue next time. Okay? That's all from today.